Cauchy-Schwarz inequality. Definition: let V be an Euclidean space. Let V be an Euclidean space and alpha beta belongs to V. Then modulus of inner product of alpha beta less than equals to norm alpha into norm beta, and the equality holds if alpha comma beta are linearly dependent in Euclidean space V. Now proof of this theorem. What we have V is an Euclidean space and alpha beta belongs to Euclidean space V. Now there exist three cases of alpha beta. First one is if alpha equals to null factor or beta equals to null factor, or both alpha and beta both equals to null factor. Therefore inner product of alpha beta equals to 0 and norm alpha norm beta equals to 0. That implies modulus of inner product of alpha beta equals to norm alpha into norm beta. So the equality hold. Now second case 2. Now the second case, let alpha beta be both non-null and non-null vector and linearly dependent. Therefore alpha equals to k beta for some k belongs to real number with k not equals to 0. Therefore LHS equals to modulus of inner product of alpha beta equals to modulus of inner product of k beta comma beta equals to mod k into norm beta square. RHS equals to norm alpha into norm beta equals to norm of k beta into norm beta, that is equals to mod k into norm beta square. Now we can see that LHS equals to RHS. Therefore inner product of modulus of inner product of alpha beta equals to norm alpha into norm beta. Therefore the equality holds. Now case 3. What is case 3? Let alpha and beta be linearly independent. अगर अल्फा और बीटा दोनों linearly independent होंगे, therefore alpha not equals to k for all k belongs to real number. This implies alpha minus k beta not equals to theta for all k belongs to real number. That implies inner product of alpha minus k beta comma alpha minus k beta is greater than 0 for all k belongs to real number. That implies inner product of alpha minus k beta comma alpha minus inner product of alpha minus k beta comma k beta greater than 0 for all k belongs to real number. This implies inner product of alpha minus inner product of k beta comma alpha minus inner product of alpha comma k beta plus inner product of k beta comma k beta is greater than 0 for all k belongs to real number. For all k belongs to real number. That imply inner product of alpha alpha minus 2k inner product of alpha beta plus k square inner product of beta beta greater than 0 for all k belongs to real number. That's imply bk square minus 2ak plus c is greater than 0 where b equals to inner product of beta beta, a equals to inner product of alpha beta, and c equals to inner product of alpha alpha. Therefore bk square minus 2ak plus c equals to 0 has no real roots. That imply discriminant is less than 0. That's imply 4a square minus 4bc less than 0. This imply a square less than bc. This imply inner product of alpha beta square less than norm beta square into norm alpha square. This imply modulus of inner product of alpha beta is less than norm alpha into norm beta.